Is everybody here? Almost time. So there's been a change of plans. Originally planned was more Python tutorial, but we felt that we're getting diminishing returns from the Python reminding, and I think practically, there's a lot of stuff to cover in the quantum mechanics department, so that might be a better bang for our buck. So today I want to pick up where we left off last time. Last time we introduced the qubit as this two-state system. I think it's black. As this alpha, this beta, like this. So we're going to ask the question, what are all the possible values that these alpha and beta can take on? Last time we also saw our first couple of transformations of these alpha and beta, of those qubits rather, which was the sort of X, the NOT gate. So we're going to first understand the space. What can a qubit be? What are the restrictions on it? How many dimensions is this space? And then we're going to see what these different operations have and pick some notable states, and at the end we're going to play a game. You have this to look forward to. Quantum Touchdown. So hopefully we'll have time to play it today. If not, you'll play it next time. So the first thing to note, if it wasn't clear from last time, is that alpha and beta are both complex numbers, which means that this state vector psi lives in this space, C2. So there's sort of an axis of the coefficient for the 0 state, and there's an axis of the coefficient for the 1 state. And it lives somewhere in here, and it has coefficients, which are complex numbers, which means that despite this looking like 2 dimensions, it's actually 4-dimensional, right? Alpha and beta, alpha for instance, can be written as something like this. So first a reminder, I'm not sure quite how much math to assume. I'm sure you're all familiar with complex numbers, but maybe as a quick reminder, we can represent, so this is our picture of C2, but let's draw a picture just of the complex plane for a moment. So we have our real and we have our imaginary axes. And, sorry, give myself a little more room. Real and imaginary axes. So points in the planes, complex numbers are points in the plane, and they can be represented in this form that I've said, so sort of the real part and the imaginary part, but they can also be written in what's called the polar representation, where we write them as some sort of like length from the origin and some sort of angle or phase. So what is the equivalent way of writing this number in terms of these guys? Is this familiar to people? I can write it as the sort of magnitude of this number, the absolute value of z, times e to the I phi. Of course, if you don't remember, there's this wonderful Euler identity where e to the I phi is cosine phi plus I sine phi. So this itself is a complex number, right? And phi is just the sort of angle around like this. So this by itself just traces out the unit circle of the complex plane. I'm not sure how much of this I need to review, but okay. So we can write this state in the polar representation and sort of make manifest all the degrees of freedom, because we say it's a 4-dimensional space where this lives. So I'm going to write this as phi equals, let's just call it a e to the I gamma times the 0 state plus the coefficient b e to the I delta times the 1 state. So I've just re-parameterized this, but now it's all in terms of real numbers, rather than 2 complex numbers. I have 4 real numbers. Haven't done anything yet. And now that we have it in this form, I'd like to introduce the first piece of important postulate from quantum mechanics. In this,
so phi is like just 1 qubit, right? That's like describing the state of 1 qubit.
This,
yes.
So this is psi, and psi here is 1 qubit. So 1 qubit, thank you for this question. 1 qubit is to say that you have a 2-state system. A qubit is not the state. A qubit is the, pardon me, the qubit is not like the 0 state or the 1 state. So we don't have 2 qubits here, we have 1 qubit, which itself is some combination of these 2 states. That's what it means. In the same way that a bit is not just a 0 or a 1, it's sort of the thing which could be either a 0 or a 1, right?
Okay.
Does that make sense?
But with complex coefficients.
Yes, but the difference with a qubit is that the coefficients are complex. With a bit, if I were to write a classical bit in this way, I would write something like, basically I have the 0 state of the bit, or of the classical bit, which I'm writing it with the ket notation. By the way, we'll talk more about this Bloch notation, I think, in the future. I'm going to kind of gloss over that for now. This just means something which we're labeling 0. The classical bit, if you insisted on writing it in this way, has only 2 options, right? It can either be all of the 0 and none of the 1, or it could be none of the 0 and all of the 1. The qubit is distinct in that it can be combinations of the 2, which differ from these Boolean options. You have only 2 options here. Here you have, well, what appears to be a 4-dimensional space of options, but we'll soon see. The purpose of this lecture is basically to show you the 2 constraints, or ways of interpreting it, which actually reduce that number to 2 dimensions. Yeah, any other questions? So in quantum mechanics, we have something called the Born rule. This tells you, given a state, what is the probability of observing a certain outcome. So it's basically this. The probability of observing something x is the modulus squared of this object. Okay. So now, this may be your first time seeing this so-called Bloch notation. Again, I'm going to leave this for Professor Machev to explain to you in more detail. I'm sure he will spend a lot of time talking about this. But for our purpose here, what you have to understand is that this inner product, it's basically it can be read something like this. The transpose vector of whatever the state x is, dot product with whatever this vector psi is, if we were to write it in the vector notation from last time. But the upshot here, I'm going to skip over those details and tell you the upshot is that the probability of observing the 0 state here is just the mod squared of this guy. So again, what this is saying, okay, likewise, the probability of observing the 1 state is the mod squared of this guy, b e to the I delta squared. So if you want to know the probability of one of the states and you've got it written in terms of those states, it's as simple as reading off the coefficient and taking the mod squared of it. Okay? So these probabilities should be real numbers. These are in general complex numbers. So mod squared, which is the thing times its complex conjugate, is always a real number. So in this case, I'd like to now ask, can I simplify this? Okay, so again, we're assuming a bit of familiarity with dealing with complex numbers here. So one thing is that the mod squared operation has this property. I can say the mod squared of the product is the same as the product of the mod squareds. And now I have another question, which is, what is that? 1. Because basically, this thing traces out the unit circle in the complex plane, which is all the points which are 1 away from the origin. So this thing is always 1. It's just sort of a rotation. Okay, so that just goes to 1. So this is just a squared. And a mod squared is just the same thing as a squared, since it's a real number. Likewise, this is b squared. These are mutually exclusive and independent, or not independent, what's the, exhaustive, mutually exclusive and exhaustive, so they should add to 1. So since we either will observe 0 or 1 when we measure it, we have that a squared plus b squared equals 1. To be otherwise would be to say that you have a probability of observing something which is different from 1. You know you're going to observe something, so that this is required basically by the laws of probability and by this Born rule. So this is what we mean when we say a state is normalized. Another way of saying it, by the way, is saying this, that thing has to be 1. But again, for those who aren't familiar with the Bloch notation, we'll come back to this. The only important fact here is that we have a constraint on these two numbers. They have to satisfy this property, which means that I'm going to write this. It's right here. Okay. Which means basically that whereas before, in general, we thought we could be anywhere in 4 dimensions in this complex C2 space, we know we're actually sort of on the unit ball in that space. So all the states live on this ball. So it's actually the 3 sphere, which means that its surface has 3 dimensions. It lives in 4 dimensions. It's a subset of this space. Kind of hard to get your head around, but you can see here that you have 4 things that can change, A, B, gamma, and delta, but that there has to be 1 constraint. So we can make that constraint explicit by reparameterizing it. So I'm going to introduce what I call the Bloch parameterization. And the Bloch parameterization says, let A be the cosine of theta over 2, and let B be the sine of theta over 2. And we'll let theta run from 0 to pi, inclusive. Okay, so why do we choose it like this? The reason that we choose 0 to pi might seem a little strange, but that will become clear later. But given that, we want in one extreme of this range to have the pure 0 state, and on the other extreme to have the pure 1 state. And is that true? Let's just check. If theta equals 0, what do I have? Cosine of 0 is 1, and sine of 0 is 0. So therefore, this would correspond to what state vector? Yes, the 0 state, yeah. So it would basically be 1 times, so this state, right? Plus 0 times the 1 state. So this is the pure state vector, which is all 0. And on the other extreme, you can also imagine if I plug theta equals pi, so maybe this is an exercise in how well you can do this in your head real quick. Cosine of pi over 2. Or just an exercise in knowing what needs to be here for this to make sense. Sine of pi over 2? 1. Yes. So in this case, this would just be the 1. So this basically interpolates with 1 value, theta, between the 0 state and the 1 state. Okay? So let's write our qubit again in all its glory. Cosine of pi over 2 e to the I gamma 0 plus sine pi over 2, or pardon me, theta over 2, e to the I delta is the 1 state. So this is our parameterized qubit. Is this now all the things that the qubit can be? Yeah, I mean, we've basically baked in that it's now explicitly normalized. Never mind this, the over 2, I guess we've seen why that needs to be there, so that theta can go on this range and hit all of the values of the 0 state, to mixtures of the state, to the 1 state. I guess what I should have done here is said, oh, if we plug in theta equals pi over 2, what do we get? We get the sort of 50-50 state. We get coefficients of 1 over root 2 for both of them. Let's just write that down real quick explicitly. If theta equals pi over 2, A would be equal to what? 1 over root 2. And B would be also 1 upon root 2. And psi would be equal to what? Yes? I don't know why I'm asking these questions if I'm not going to take the time to listen to answers. Okay, so we would get this state. And now if I told you we had this state, exercise in the Born rule, what's the probability of getting state 0? Half, right? Because it's the square of 1 over root 2. So that's square, and likewise it's the same for 1. So this is the 50-50 state, right? So we can see that this is the reason we write it this way. But this isn't exactly the Bloch parameterization yet. And the reason is we still have an overall phase. What does that mean? Okay, so important fact. In quantum mechanics, global phase does not matter. So what does this mean? By global phase, I mean multiplying the entire state by something which is of this form, e to the I times some number. That's a global rotation in the complex space. I'm just taking all my numbers together and rotating them. It doesn't matter in the same way that when you're working with a potential, say my electric potential here is 1 volt, my electric potential here is 5 volt, or 0 volts and 5 volts. You may know that what I label this doesn't matter, right? I could call this 100 volts, and I could call this 105 volts, and the physics would be exactly the same. You have a choice of labeling, and that's called gauge freedom. So actually, in particular, global phase is a gauge freedom. Okay, let's see mathematically why that's true. Consider the state. So I'm claiming that the state psi is physically equivalent to the state e to the I chi whatever times psi. Okay, so if I put any factor like this, they're physically equivalent. Let's see why. Well, maybe I want to measure the probability of x if I have that state vector. Well, according to the Born rule, I set this up. X inner product with that guy squared. But what I would actually write down, sorry, pardon me, inner product with e to the I psi, or chi is what I'm writing. And for the same reason as before, this constant multiple can be moved outside of the mod. And this thing equals e to the I psi squared times x psi. And once again, that is just 1, that's unity. And we are left with the probability of x given this other state. So basically, any overall phase, when you plug it in and calculate probabilities, doesn't matter. In the same way that any other gauge freedom doesn't matter. It's just a choice of what to call something. So you can see that in this parameterization, I have a phase here, and I have a phase here. But I can freely multiply and divide by any phase I want, which means multiplication or division by something of the form e to the I, whatever. So I'm going to fix my gauge. And this gauge terminology is, good for us high energy physics people, but what we really mean is we're just going to choose a convention. So by convention, choose basically choose a phase such that, how do I want to write this? I'm going to say choose alpha such that, how do I write this? Alpha is real and alpha is non-negative. Okay, this is essentially saying, let's just choose our phase such that this guy doesn't exist, that this gamma here is 0. Does that make sense? Let's pause here for some questions. I feel like I've gone kind of fast through this, so anyone maybe a little bit unfamiliar with this might have some very good reason to be confused. So maybe. Okay. Feel free to interrupt me if you think of a question. So what does this mean? Basically, I'm going to take my psi as I've defined it here, and I'm going to say it's equivalent to e to the minus I gamma times the thing I defined, right? These things are equivalent, right? That's the setup here. This is going to be important a little later. You can multiply freely by any number, any complex number, as long as it has unit modulus. So as long as it's just e to the I something. Again, that's as long as it's on the complex unit circle, which I've been saying that a lot, so let me just have a visual to point to. So these are things like 1i minus 1 minus I, and everything in between, like this point here, 1 plus I over root 2. These are all things with unit modulus. These are concretely what the phase could be. Does that make sense? I'm just a little worried there's someone in here who's confused and isn't saying so. So this is what phases can be, any point on this circle. And again, it doesn't have any impact on what you actually measure. It's just what you call it. So these two are equivalent. And here, let me substitute what I just wrote here. And I get cosine theta over 2. The e to the I gamma here is multiplied by my e to the minus I gamma. E to the 0, just 1. So that drops out. That was the point of this. And then I get sine theta over 2, e to the what? Well, I had e to the I delta, and then I subtracted e to the I gamma, basically, right? Let me write that as e to the I delta minus gamma, 1. And so I've consolidated now my two spurious degrees of freedom into one relative phase. So let's say this is the relative phase, and define that as psi, or phi, pardon me. So this is the real Bloch parameterization. I'll write it one more time. Pardon me. Sorry, it's like a mouthful to write in some sense. Okay, so does that make sense? So let's look now at what this actually is. We actually have two parameters, theta and the relative phase. So essentially, what looked like 4 dimensions of freedom before was really 3 because of normalization. And then one of those degrees of freedom is totally spurious. It's just some, gauge freedom. What we really have is only the relative phase. What did I say I was going to do? Bloch sphere. Okay. So this parameterization lends itself nicely to this visualization on the Bloch sphere, it's so-called. So if you take the complex plane, C2, and you mod out by this normalization, let's call this S3, and now if you mod out again by by a global phase, you get what's called, for the math topology nerds out there, CP2, the complex projective space of 2 dimensions, which turns out to be isomorphic to the unit sphere in 3 dimensions, S2. So this actually is now a sphere. And we're going to draw that sphere. And maybe we'll put it over here. Okay, make this a good one. Okay, whatever. Okay, so here's our sphere. And we'll choose to represent theta as the polar angle. How far are we down from the top? And we're going to label the axes like this, x, y, and z. And we're going to choose to represent phi by how far are we clockwise of x as we wrap around the z-axis. Okay. Now we're going to plot some notable states. Okay, so where do I want to put this? Okay, so we've already said that if theta equals 0, we get what state? We get psi being, I'm going to actually make this like a little table. We're going to have the theta and phi, and then we're going to have what? We're going to have theta, we're going to have phi, and we're going to have what state you get. Does that make sense? So if theta equals 0, what state did we get? The 0 state, right? And where does that live? It's the North Pole. And what does phi have to be? In other words, what's the latitude at the longitude of the North Pole? It's degenerate, right? You can call it whatever you want, and they all correspond to the same point. That's how we know it's a sphere. Well, that's another way we know it's a sphere. So this can be any, sort of undefined. The South Pole corresponds to theta equals pi. Again, it doesn't matter what phi is. Although, did we show that? Actually, I have to show that. Let's plug this in one more time. Let's do this exercise one more time. Theta equals pi. I brushed past this actually the first time, and no one caught me on it. If theta equals pi, what does this Bloch parameterization tell us psi is? Psi equals what? Well, indeed, if I plug in pi over 2 to cosine, this drops out, right? And this becomes 1, but we still have this, right? So what do I have explicitly? So I'm plugging in pi over 2 here. Sine of pi over 2 is 1. So I have 1 times, so I have e to the I phi times the 1 state. So I claimed before that this was the 1 state, but it's actually e to the I phi times 1 state. Is it the same thing? Yes. Why does phi not matter here? Because that phi is only a global phase, right? So we can safely just ignore it and say they're all equivalent. So indeed, the phi doesn't matter here at the South Pole either. That's the 1 state. Okay. What about if theta equals pi over 2? Well, where would we end up if theta were pi over 2? Well, that's the equator. The xy plane, exactly. It's the equator of the circle. Yep. Thank you. Exactly. And so now it actually does matter what do we call this? Phi is. So let's say phi equals 0. What state do we get? Well, we have to plug it in. So all of these cosines and sines of pi over 4 are 1 over root 2, as we said before. So what we end up with is 1 over root 2, we'll factor that out, times the 0 state, plus e to the I phi, which e to the I 0 is just 1, right? So, okay, so this is the state like this. Again, what we had in here was e to the I times 0. So that's just 1. Let me just write down the other 3 real quick. We have pi over 2, pi over 2, pi over 2, pi over 2, pi, 3 pi over 2. Right. So we're going to do these 3 others real quick as well. What do I get here? So they all have the 1 over root 2 out in front. Factor that out for all of them. They all have what phase on the 0 state? Again, the phase is the complex e to the I something that lives in front of them. And what's in front of the 0 state every time? By convention. 1. We're choosing a convention basically so that the thing in front of the 0 state is always real. Technically, it's pi over 2 because that's the cosine, right? Oh, sorry. Technically, it's 1 over root 2. That's from the cosine. But the phase is always just unity. So these I can just safely write like this. So the only thing that's changing between these states is the thing that goes in front of the 1, the phase in front of the 1 state. So what are these phases? Well, we should look at our complex unit circle. If the argument, this is theta, this is phi, right? Is that angle? So if the angle is 0, I get 1. If the angle is pi over 2, 90 degrees, I get I. So I'm basically taking this thing and putting it like this. So I get, here I get I, here I get -1, and here I get minus I. And we have special names for these states. I mean this to, I'm defining in this direction. We call this the plus state, we call this the I state, we call this the minus state, and we call this the minus I state. Why do we call them this? Well, it's basically just labeled by what's right here, right? We have plus, here we have I, here we have -1, and here we have, or here we have a -1, and here we have minus I. Sometimes this might be written as plus I as well, I don't know. So these are our 6 states. Let's plot where they live on the Bloch sphere. This is the plus state. This is the theta equals, or pardon me, theta equals pi over 2, phi equals pi over 2. This is the I state. This here is the minus state, and this is the minus I state. So these are our 6 friends, these states. And of course there's a 2-dimensional manifold of all the states in between. You can have some combinations of these things and so on. But these are all the things that the qubit can be. It can be anywhere on this sphere. And we've seen that there's no other options that are physically distinct from the points on the sphere. So that answers our original question, which is what things can the qubit be? Now I'd like to ask the question, what about these transformations? In particular, last class we saw the X gate, or the X operator, which had the behavior of swapping 1 and 0 states. I'd like to know for these operators, and some other operators we're going to introduce in a moment, what do these do to these states? So, take a picture of the board because it may be helpful for Constantine. So we saw that the X operator behaves by swapping 0 and 1. what do you think it does to these other states? Remember, it could be written as this. So we could apply it to these other states as well. Again, remember our convention is basically that we can write things like this. Let me just call it A0 plus B1. We're sort of saying that these things are the same. This is just our other way of writing it, right? So two different ways. So if I want to write the plus state here, let's write the plus state. What would the plus state be? Well, it'd be 1 over root 2, 1 over root 2. What happens when I do this matrix multiplication? It's left the same. So basically it fixes the plus state. So x on the plus is just the plus. Similarly, x on the minus state well, actually, what is x on the minus state? Well, it's this state, right, before. So I've just edited it. Does that make sense, why this is the minus state? If we look over there, it's 1 over root 2, 0, minus 1 over root 2, 1. So I put a minus 1 over root 2 here. If I switch these, I actually get this. Uh-oh, that's not any of our states that we're familiar with. What is this? It's still the minus state. Why? Because this is minus the minus state. And this minus there is a phase. In particular, it's e to the I pi. So this is physically equivalent to the minus state. So I can safely say that it actually fixes the minus state as well. And it turns out, let me just, for the sake of time, write the effect that it has on the I state and the minus I state. It actually flips those. So it leaves these the same, but it flips these. So if I can draw this, basically what it does is yes, right. It takes this guy to here. 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 And it leaves these guys fixed. I argue that this can be interpreted as a rotation by 180 degrees about the x-axis. And it turns out it can be. Likewise, we have another gate called y. The y gate is the poly y matrix, like this. What do you think would happen if I go through all the calculations and figure out what this does to everything? Well, I'm not going to go through them all right now, but if you calculate it, you'll find out that this is the same as rotating the sphere by 180 degrees about the y-axis. So it takes, again, y acting on this state, maps it to this state. Y acting on this state maps it to this state. It leaves the I states fixed. The I and minus I are the eigenstates of the y operator, believe it or not. Likewise, z rotates around z. Okay, so we are almost set up. Let's look at one example with z. Okay, so I think we're probably not going to have time to play the game, unfortunately. But I am going to just show the game, and then Constantine will be very excited that he gets to be the one to show you the game. But I just want to introduce it pedagogically. So the game is this. Huh? Oh. Okay. Well, maybe I think that'll cycle through and find itself. All right, sorry. Let me keep moving while that thing sorts itself out. The Z is the poly Z matrix like this. Let's just run through one example of this operator. Let's compute Z acting on, I don't know, what should be an interesting one? Let's do the plus state. Z acting on plus is what? Well, I can compute it like this. 1 minus 1 times 1 over root 2, 1 over root 2. And for the same reason as before, I get 1 over root 2 minus 1 over root 2, which is the minus state, right? So apparently z acting on this is the minus state, which jives with our thing here, because if I rotate this quick look, it should go to the minus state, right? All right. Here's what I wanted to show you. This is our game, which sadly we will not have time to play. It's called Qubit Touchdown. It's a quantum computing board game. And all I'm going to do is show you the board, and next time you will play it and talk about it. So the board is this. It's you have 6 states that the board can be in, and those are the 6, states that we drew on the blocks here. And we have all of these things that the all of these letters, which correspond to operations we can do. So the really fun part is that we have cards, which are the operations. So the identity operation, S, which we haven't explained yet, H, which I'd like to explain now if I may. And these operations move us between the states. So we can see, hello, focus please. We can see that X and Y both switch between the 1 and minus 1 states, which makes sense because that's top and bottom. X and Y doing this or doing this switches to top and bottom. But now we need to understand all these other gates. And these will basically be the building blocks of our quantum computer. These, just like NAND gates and AND gates and other logical gates for classical computers, these operations are the building blocks for our quantum computer. Okay. Any questions before I show you the Hadamard gate? Okay. I think we can do this in the next 6 minutes or so. So it's this, and we can ask the same question, what does this do to our states? And the most important thing that it does is, what does H do to 0? Well, we can compute this by doing 1 over root 2, 0 state is like this, and we compute it, 1, 1. So we get 1 over root 2 times 1, 1. Which is what we call the plus state. So it sends 0 to the plus state, and it sends, I'll state without proof that it sends 1 to the minus state. And then let me also state without proof 2 more things. It sends plus back to, you want to compute this one? Let's compute this one. 1 over root 2, 1, 1, 1 minus 1, 1 over root 2, 1, 1. So we have an overall 1/2 out front. What does it do here if I multiply this? 2, 0. It's an ugly prime, sorry. Sorry you had to see that. Okay, so that actually undoes it and it sends it back to the 0 state. And then one more time without proof, you can compute all these things till you're blue in the face. It sends that back to the 1 state. So with this in mind, I can't help myself, I'll be complete. It actually leaves, it sends I to minus I, and it sends minus I back to I. So given all this information, can you figure out how we can represent the Hadamard gate as a rotation? Let's draw in another color the operation of the Hadamard state. it sends, okay, ignore the blue stuff. That was the x. It sends 0 to 1. It sends, or pardon me, 0 to plus. It sends plus to 0. It sends 1 to minus, and minus to 0. And it sends, I'm going to be a little bit evocative with the way I draw these lines here. It sends this here and this here. So where do you think we're rotating the sphere about?
Somewhere 45 degrees between x and z.
Yes, that's exactly right. We are rotating between an axis which lives 45 degrees between x and z. And maybe I can draw this reasonably well with the perspective and all. Now, that's not a straight line. This is the axis of the Hadamard. The axis of the Hadamard is x plus z. These unit vectors are root 2. And it's rotating them about this thing. So every operation basically corresponds to some rotation on the Bloch sphere by some angle about some axis. And the reason I say that the Hadamard is so important, by the way, is that it's really the basis for all the things where we want to build superpositions. Generally in quantum computers, we start out with qubits in the 0 state, and we want to put them in a superposition. The best way to put them in a superposition is by acting a Hadamard on them. Now they're in this state. Once again, the Hadamard state acting on 0 is 1 over root 2. That's the superposition state. That's what we're doing all the time. It's the first step in most of these quantum algorithms that we're going to look at. Okay, so this is the Hadamard. There are several other gates on this board that we didn't look at. There's the square root x gate, which basically, if you're not familiar with square roots of matrices, it's what matrix, when acted twice, does the same thing as x. Can you tell me what rotation, which I could do twice, would be the same as x? The x rotation, again, is in 180 degrees around the x-axis. What's half of that? 90 degree rotation around the x-axis. And indeed, on this thing, I can see that the x cards, the root x cards that I get, will map 1 to I, they'll map I to 0, 0 to minus I, and minus I to 1. So that's exactly right. 2 more that I'll throw out there. Oh, actually, we have the Hadamard, which we've covered. And the last one that's on here that you're not familiar with is the so-called S gate. S is a 90 degree rotation around the z-axis. And it has, here's a challenging question. What do you think the matrix for S must be? It's the thing that if you do it twice, you get the z. Basically, what thing can I apply twice and get z?
1, 0, 0, minus I, or I.
Exactly, yeah, 1, 0, 0, I, and I guess minus I would also give you the same thing, but it would be different from an overall phase, and therefore the same. So, so you get, oh, what I said was not true. The minus I would be rotating the other way. So actually, sorry, that was totally fake what I just said. I was lying. You're correct that there's 2 solutions because there's 2 ways I can get 180 degrees around. I can go clockwise or counterclockwise. What you said was just the counterclockwise one. This is the clockwise one. So yeah, you're exactly right. So this corresponds to these, and just to verify here, S will map minus I to plus. Does that sound right? Minus I to plus. Yes. Okay, so now we understand all of these operations. So when you come back, you can play this game. And we're basically out of time. So are there any questions? Let me leave you with one last little piece of information. What do you think is the formula for the arbitrary rotation around an axis by an arbitrary angle? If I define an axis by stating a normal vector, n, x, n, y, n, z, call that n hat, what do you think is the equation for that operator that goes around that clockwise by pi, or pardon me, by an angle theta? It's this, turns out. This is the matrix exponential, so that gives you another matrix if you're not familiar with matrix exponentials. And one thing I really love is the notation that we sometimes use. So these x versus the sigma x, sometimes interchangeable, depending on the context. But this is often written, this will be the last thing I write, pi over 2, n hat dot, the vector of these matrices. I just think that's a really fun construct, the vector of matrices. So these are defined to be the same. All right, so that's the thing. And by the way, this 2 is the, reveals a very deep fact, which is that SU2 covers SO3, double covers SO3. So ponder that if you're interested. All right, thank you all for your attention.